Hello, everybody. Thanks for listening in on our session today. I'm excited to be presenting back at Spark Summit, and I hope everybody's staying safe and healthy in the current environment. Today, we're going to talk to you about how we've achieved scale for our follow recommendation system, which is one of the most data intense systems at LinkedIn. Our follow recommendations power or give recommendations for members to follow or connect with multiple entities, and we'll get into more detail about that later on in the talk. Today, you'll get to understand or get more detail about how our follow recommendation system works, and also about our innovative 2D partitioned hash join algorithm that allowed us to achieve scale. Today, we're going to be going over an overview of follows relevance and the objective that we're striving for in our follow recommendations product. And then I'm going to hand it over to Emily. She's going to get into more detail about our offline scoring architecture and dive deeper into our 2D hash partition join algorithm that allowed us to achieve scale. So, and to start it off with an introduction of follows relevance system. Before we get into actually detail, I'd like you to experience for the recommendation system at play. So if you can take a moment opening up your app or going through to linkedin.com through your browser and clicking on the My Network tab, which is one of the main placements our follow recommendations appear in. They do appear in a lot of other placements, but this is the most prominent one. So you can get a feel of how the recommendation system works. Follow recommendations is actually owned by the community's AI team. And the mission of our team is to empower members to form active communities around common areas of interest so they can have conversations. We've distilled the problem into three main areas. One is discover, which is empowered by the follow recommendations and will be the main focus for our presentation today. The second one is engage, to allow members to join conversations after they've followed entities that share their interest. And then finally, when the members are ready to contribute, to assist them to reach the right audience, for example, using the appropriate hashtags. There's more detail about what our team does in the blog post that I've linked below, and also our Rexis industry session presentation. So the follow recommendation system, like I said, recommends entities, which can be members or audience builders, pages like company pages, events, hashtags, newsletters, groups, to our members or the viewers of those recommendations. Now we have hundreds of millions of members and millions of entities, so this creates a key challenge or a scaling challenge. We have hundreds of trillions of possible pairs. So the follow recommendation system allows us to navigate this scale and recommend the best entities or the most relevant entities for a member to follow. The way we define what is most relevant or the best entities, or in other words, our recommendation objective, consists of two parts. First, we want to recommend entities that the member finds interesting. So that means we want to increase the probability a member or a viewer is going to follow an entity, given that we've recommended that entity to them. And then we want them to engage with the content that's produced by that entity after the member follows that entity. So the act of following or forming an edge actually creates a lot of content that shows up in members' feed, and that actually those follow edges contribute a big chunk of the engagement that we see on our LinkedIn feed. So it's a very important piece of our content ecosystem. More concretely, the mathematical formulation for our follows objective function has the two components: the probability of a follow and the engagement or the utility after a follow edge is formed. And there's a tuning parameter that allows us to trade off or to combine those two quantities in an optimal way, and that's controlled by our alpha parameter here. So this score is what defines the final ranking that the viewer or the member sees from the follow recommendations. So with that, I'll hand it over to Emily to give you more details about our offline scoring architecture and our 2D hash partition join algorithm.
All right, thanks Abdul for this introduction. So in this section, I'm gonna talk about the offline scoring architecture that we have in Follows Relevance and the scalability challenges that we faced. So first of all, in Follows Relevance, we need to generate recommendations for the entire LinkedIn user base, so more than 690 million members. And we need to make the distinction between two types of users, and I'm going to explain why in a bit. So first, we have the active members, who are LinkedIn users who have performed recent actions on LinkedIn. And the inactive members on the other side are either brand new users to LinkedIn or users who have registered in the past but haven't really used the website or the LinkedIn app recently. And so obviously for active members, we have a lot of data about their past activity. They have a full profile, so we can leverage that to generate personalized recommendations. However, for inactive members, we'd love to generate those personalized recommendations as well, but because we don't have enough data, we have to fall back to the segment they belong to generate recommendations. So obviously, to generate personalized recommendations, we need a very heavy Spark offline pipeline to pre-compute those because the recommendations are going to be keyed by viewer. On the other hand, for inactive members, the offline pipeline is a lot more lightweight because the recommendations are keyed by segment. So in the rest of the presentation, we're going to mostly focus on the scalability challenges related to the generation of personalized recommendations. But before that, I wanted to show you what the end-to-end pipeline looks like for active members and how the personalized recommendation integrate into this pipeline. So you can see first that we have the pipeline is split into the offline parts where all the pre-computations happen in Spark. And everything at the top of the slide in yellow is everything that happens online in real time whenever a client calls us to get follow recommendations for viewer X. So we run the offline flows on a regular basis, and we push the recommendations to key value stores, which make the communication between the offline and the online. And so you see here in red where the pre-computed personalized recommendations are pushed. And so whenever a client calls us, we first query this key value store to fetch the personalized recommendations. However, I think it's interesting to mention that we do not exclusively use those personalized recommendations because obviously those are pre-computed and so do not take into account the very recent activity of the member. And so in addition to those recommendations, we also fetch what we call contexts of the viewer, which are real-time signals of the activity that the viewer just performed. So for example, if the viewer just interacted with a post or just followed an entity. And so based on those contexts that are queried in real time, we fetch additional pre-computed recommendations, which are context-based. And so at the very end, we merge those two sets of recommendations. We do a final scoring, filtering, and blending, and return those ranked recommendations to the client. So once you have the understanding of the whole end-to-end pipeline, now in the rest of the presentation, we'll focus on the pre-computation of the personalized recommendations that happens offline. So let's take a look at the different feature categories that we use to generate those recommendations. We have three main categories of features: the viewer features, the pair features, and entity features. The viewer features reflect the general consumption behavior of the viewer. So for example, how many times the viewer comes to the website, when he or she sees updates, how many times we interact with the updates. And in addition to that, we also leverage the profile information of the viewer. So industries the viewer belongs to, country he lives in, and so on. Similarly, on the entity feature side, we have the similar features, except that we focus on the creation side. So how many times an entity posts something on the feed, for example, how many viewers interact with those updates, and so on. So we have a fairly small number of viewer features that we generate, a medium number of entity features, but the most valuable features that we generate are the pair and interaction features, and those are generated in very large number. So I'm not going to go into the details of which pair features we generate. I just added some examples here. So basically, we can use the viewer entity past engagement, but we can also derive viewer entity affinity features based on graph data or based on browse map scores. We also leverage embedding features and many more. So with that in mind, so we need to generate those features for all viewers and all entities. So we have millions of distinct active members. We also have millions of recommendable entities, including all the entity types that Abdul mentioned previously. So members, companies, hashtags, newsletters. And so this means that potentially we would need to generate pair features for trillions of possible viewer entity pairs. This would require a huge amount of resources, and this is obviously not possible for us. So as a first step, we apply a candidate selection based on some pair feature values. Not going into the details of the candidate selection, but at the end, we still end up with hundreds of billions of viewer entity pairs, which is still a lot. So the main challenge becomes how can we join all those features together and meet an acceptable runtime performance? The first very naive option is just to do a three-way Spark join. So you have the three features tables, and so you could first join the viewer features to the pair features. Because those tables are not pre-partitioned, the default join is the shuffle hash join in Spark that would be done on the viewer ID key. And this would generate hundreds of terabytes of shuffle. And once you have this first intermediate table, then you would also need to apply a second join with the entity features, this time using the entity ID key. And this, again, generates hundreds of terabytes of shuffle. And on top of that, this join is very skewed because some entities are recommended more often to viewers, for example, the popular entities. And so this creates a lot of skewness and some tasks running longer than others. So this option was prohibitive for us. It was too expensive. So the second option, which is the one we initially adopted in Follows Relevance, is the partial scoring using a linear model. So let me explain what this is. In the picture, you recognize at the top the three features table: member features, pair features, and entity features. And so the idea is, instead of joining all the features together, to try to reduce those inputs as much as possible so that the three-way join becomes manageable. So the idea is to directly score the viewer features in a separate job to generate a score. And so the way we do that is by, because we have trained a linear machine learning model, in our case, a logistic regression, we can extract the viewer specific coefficients from the model and directly score the viewer features to generate a single viewer partial score. We can do obviously the same thing for the entity features, generate a single entity partial score, and for the pair features. And so instead of having to join all the features, now we only have to join tables that have 2 or 3 columns. So basically the viewer ID and the partial score. And so this is a lot more lightweight, requires a lot less memory. So this is a manageable three-way join. This is an acceptable solution, but it has some disadvantages. First of all, there is a lot of scoring overheads and a lot of intermediary outputs that are generated. Each partial scoring job outputs its data to HDFS, and then we load those again to join the scores. And we have to apply this pipeline to each single term in our objective. So here you see the p-flow scoring, but we do the same thing for utility scoring. And it becomes more complicated with the number of models that what we need to score with. But maybe the main constraint that we have here is in terms of relevance, we are forced to score with a linear model. So because we need to do a partial scoring, we cannot score with non-linear model. And so this was a big constraint for us. And so a year ago, we started the big refactoring project of the offline scoring pipeline, trying to make it more scalable, but above all, trying to remove the constraint of scoring with linear models only. And so this was made possible by the adoption of the 2D hash partition join. So let's quickly go back to our main challenge here. So we have those 3 tables, hundreds of billions of viewer entity pairs, and we need to join all those features together. And so we've seen in the previous section that the main bottleneck is the very large and wide table of pair features with a very skewed entity distribution. So we cannot really manage to shuffle those data. This is really prohibitive. So in this case, the new question becomes, can we manage to join all the features together, but without having to shuffle the pair features twice, once on the viewer key and the second time on the entity ID key? And so we have developed a solution in collaboration with our Hadoop team at LinkedIn, which is the 2D hash partition join. So the key idea behind the 2D hash partition join is to do a smart partitioning of the 3 features tables. So if we look at the picture on the right, imagine that we have repartitioned the pair features table, and for each single pair partition, we are able to figure out which is the corresponding viewer partition that we need to load into memory, and similarly the right entity partition that we need to load. This way, we just need to load those 2 partitions and perform a local join for all the records in the pair partition. So this is the idea behind the 2D hash partition join. So how do we partition those tables? For the viewer and the entity features tables, this is quite simple. We just apply classic hash partition. So we partition the viewer table into V partition, the entity features table into E partitions. And for the pair features table, it's slightly more complicated. So we partition it into V times E partitions, but we use a 2-dimensional custom partition function on both the viewer ID and the entity ID, which will allow us later on to join on those 2 keys at the same time. So how do we pick E and V? So basically it depends on your use case, but basically you need to pick those large enough so that every member and entity partition can be loaded into memory. So obviously it depends on your cluster resources, your input data size, and the executor memory that you want to set in your job. There are a lot of optimizations that are performed under the hood in the 2D hash partition join. So if you want to check out the blog that was written, I added the link to this slide if you're interested. So just to illustrate this partitioning logic, so for the viewer and the entity table, this is kind of simple. You just take the hash key of the viewer ID and the entity ID respectively. For the pair table, we compute the partition number using this 2-dimensional partition function. And so if you look at this equation, basically, we notice that for each pair partition P, we always have a single corresponding viewer partition and entity partition. And those can be found using those simple formulas. So P divided by E and P modulo E. So let's take a quick example. If you look at the right side of the slide, so let's take partition P equals 120. I can find the corresponding viewer partition equals to V1, the corresponding entity partition E20. And now that I know that, I can just load those partitions into memory in the single executor and perform the local join. So with that in mind, now that we have partitioned the 3 tables, how does the join algorithm works? So we first launch a mapper for each pair partition. So this is done by just calling .map partition in the Spark Dataset API. And so each mapper is going to load the entity partition as an in-memory hash map using the formula that I described in the previous slide to find the right partition to load. And similarly, we also load the corresponding viewer partition. So either into a hash map or another optimization is to use the stream reader, and I'm going to talk about it in a minute. And so once we have those 2 partitions loaded, for each pair features record in the pair partition, we can look up the entity features record by entity ID and do the same for the viewer features record and join the 3 sets of features together. And so now that all the features are brought together, we can score those right away and before storing to HDFS. So just to go back to the stream reader optimization, when you repartition the viewer and the pair tables, you can also sort by viewer ID so that when you're so that you don't have to load the viewer partition into memory, but you can use a stream reader that iterates through the viewer ID. And so this way you only have to load the entity partition into memory, and you can just use a stream reader for the viewer partition. In our case, we decided to use a stream reader with the viewer table because it's larger. Although we have fewer features, we have a lot more viewer IDs than entity IDs, so it's longer. And so after we adopted this 2D hash partition join and refactored our scoring pipeline, this is what it looked like on the right. On the left side, you have the old scoring pipeline. And so the first improvements that we see is first that we do not need to shuffle the pair features table during the join anymore. Now the tables are pre-partitioned and we can just apply the 2D hash partition join. The second improvement is that we do not have intermediate data anymore stored to HDFS. This whole logic of joining the features together and scoring those with our machine learning models happens in a single Spark job. And so we save a lot of disk space, obviously. And last but not least, the main improvements that we got from this refactoring and this 2D hash partition join adoption is the ability to score using a nonlinear model, such as XGBoost. And so this model takes into account a lot of interactions between the features and brings a lot of relevance improvements. And so to summarize the gains that we obtained after adopting the 2D hash partition join, so first in terms of runtime performance, we improved our cost to serve measured in gigabytes hours of the offline scoring pipeline by 5x, which is a lot. And in terms of HDFS storage, we saved more than 8x of disk space. And in terms of relevance, so being able to transition from a linear model to a non-linear model, so logistic regression to an XGBoost model. After running an A/B test, we measured the total number of follows going up by 17%. And the downstream engagement after following those entities was up by 11%, which is a big win for us. All right, so that concludes our presentation. Feel free to ask questions in the chat if you have some. I added my contacts and also Abdul's if you have follow-up questions. I really want to thank the LinkedIn Hadoop team, and in particular, Feng Shili, for implementing the algorithm and helping with its adoption in Follows Relevance. And finally, I just added 2 links to some interesting blogs. The first one talks about the challenges that the community AI team is trying to solve. And the second one is more engineering focused, talks about the various scalability challenges at LinkedIn across various teams and the different solutions that were developed to try to solve those. And so it includes some details about the 2D hash join in particular. All right, thanks.